Okay, so today we will discuss about complex numbers. So let's start with what we mean by I. So I is defined to be square root of minus 1 or the solution to this following equation. So note that I definitely does not belong to R. So that's our next proposition. And we prove it as assume that it did belong to R. Then we know that a square is greater than or equal to 0 for all a belongs to R, but I square equals 1 which is less than 0, hence we have a contradiction here. So I does not belong to R. So this motivates us to define a more general space which is quote unquote algebraically complete. So that's where we get the idea of complex plane. So it is a set of form where A and B belong to real number. So why is this set well defined? So we'll discuss that. Say A1 or A1 IB1 is equal to A2 IB2, then that implies that A1 equals A2 and B1 equals B2. I will leave this as an exercise for you to think why is it true. But yeah, so this defines a well defined set. Now we move to our next property. So we define addition on C as if Z1 equals A1I B1 and Z2 equals A2I B2, then Z1 plus Z2 equals A1 plus A2 plus I into B1 plus B2. And note that every complex number can be written in form A plus I B, where A and B are real numbers. This is by construction, as we can see. And multiplication on complex number is defined as Z1 into Z2 equals A1 plus I B1 A2 plus I B2, which is we can just distribute them. So that equals so this is what we mean by multiplication in complex numbers. So that said, we will look at some properties which are commutativity, that says that Z1 plus Z2 equals Z2 plus Z1 and Z1 into Z2 equals Z2 into Z1 for all Z1 and Z2 belongs to C. Uh, it is quite easy to check. And second is associativity, which says that the order of addition does not matter, or say multiplication for that matter. And the next would be distributivity, which says that our both operations are well defined on complex plane. So that out of the window, note that if Z belongs to C, then it can be represented as A plus IB. But we can also represent this as a member of R2 as A comma B, which motivates our next theorem, which says that C is isomorphic to R2 as a vector space over R. This just means that there exists a bijective function from C to R2. So proof. First of all, I will leave the proof that C is a vector space over R as an exercise for you to prove. So now define f of C to R2 as f of A plus IB equals A comma B. So note that this function is bijective. So yeah, f is a bijection, hence C is isomorphic to R2. Hence they share quite a few many properties. The first one being let Z1 and Z2 belong to C, then we define an inner product in C as this. You can check that this defines a well-defined inner product. So now we define a norm of element in C. So say modulus of Z1 equals square root of this inner product, which in turn turns out to be so yeah, this is what we mean by a norm. So in short, if Z1 is of form A plus IB, then modulus of Z1 equals square root of A square plus B square. So that out of the window, we'll move to the last part, which says that if Z belongs to C, then Z is of form R to I theta, where R is not equal to 0 and theta lies between 0 and 2 pi. So yeah, we know this from high school, so I won't go into the proof of this.